All right, students, we're going to be investigating specific heat capacity with this simulation. The directions are going to be in the handout here, which you should make a copy of. You have this in your instructions in Google Classroom to make a copy of and share with me. Or you can highlight all this stuff and copy and paste it into your distance learning portfolio. The section of the text where this is around begins on page 432, chapter 13. So specific heat, it describes how much energy is required to raise an object's temperature. Water, the specific heat has funny units because, again, if it's how much energy is required to raise a substance to a specific temperature, here is the temperature units, here is the mass of the substance, and here is the energy. So joules for energy per unit mass, degree Kelvin. That's what specific heat measures. And that makes sense. So if you're asking how much energy in joules, does it take to raise the temperature, here's Kelvin, we're raising the temperature in Kelvin. How much substance are we raising the temperature of? That's here. So even though these units look complicated, they make complete sense when you think about what it's asking you to do. These different substances have different specific heats. They have different amounts at which they can be raised the temperature of by specific amounts of energy. The specific heat capacity has an equation. The amount of energy required to raise that is based upon numbers in the table that we just saw. So if we're talking about water, then the specific heat of water is in the table right here. That's 4,186 joules per kilogram Kelvin. So that would go right here. The 4,186 joules per kilogram Kelvin would go there. The mass of the substance that you're heating up would go there. That's not going to be in a table. That's something that you're going to measure on a balance. And then the temperature change is something that you would record. This is usually an experiment that I do with my students. But the distance learning thing kind of resigns us to a simulation here. But this is our equation. Now I've given you a couple simple problems to answer just to make sure that you're reading this in the Google Classroom. But here is a problem from the text. How much energy must be transferred as heat to the 420 kilogram of water in a bathtub in order to raise the water's temperature from 25 degrees Celsius to 37 degrees Celsius? So this doesn't need to be in Kelvin in this particular case because Celsius and Kelvin are 1 to 1. So for every 1 degree of Kelvin increase, we have a 1 degree Celsius increase in temperature. So we don't need to worry about that conversion. But with that said, the change in temperature is final minus initial. And that change in temperature, change being this delta symbol right here, is 12 degrees Celsius. And because of the 1 to 1 relationship of Celsius to Kelvin, that change in temperature is equal in both scales. That would not be the case if this was a Fahrenheit transition. So we have our delta T in this equation right here. So we have that part of it. Now we just need C and M. So M is right here, the 420 kilograms of water. And the C we got from that table that I was talking about in the beginning of this video. Plug those things into this simple equation, which is above in the chapter document right here. Energy equals the specific heat of water times the mass of the water in the problem times the change in temperature. And that gives you the energy in joules. You can choose to put it into kilojoules if you want. The problem didn't specify which you would be putting it in for. So now let's take a look at the handout now that you have an idea about what specific heat is. That The handout says, describe how heat flows from hot to cold. Explain that some materials hold and release more energy than others, specific heat. So that's what you're going to see in a simulation, which we've already tinkered with. I'm going to reset this. And I'm going to put the beaker on the heater, turn on my energy symbols, and I'm going to put the thermometer inside of the beaker. And you can add energy symbols by heating it up and cooling it down. And you can compare which beaker